Welcome to my channel. Let's have a look at problem 2328 together. Number of increasing paths in a grid. This is a new problem. So for this problem and in this video, we're going to share a dynamic programming solution. As we know, when we write dynamic programming solutions, the solution can take on different formats. So here we are going to share a format which we think is intuitive. So first I'll read through the statement of the problem. Then we look at the example and analyze the method and idea. Finally, we share the code. So first, let's start with the statement of the problem. We are given an m by n integer matrix called grid, where we can move from a cell to any adjacent cell in all four directions. So we are required to return the number of strictly increasing paths in the grid such that we can start from any cell and end at any cell. So since the answer may be very large, so we return the result modulo a big number. So this is a number. So this paragraph basically explains what do we mean by different for two paths. So two paths are considered different if they do not have exactly the same sequence of visited cells. So with that said, let's look at the examples. So in example 1, so we have 2 by 2 grid, and the output is 8. So in the explanation, so it specifies the number of passes for different lengths. For example, length 1, length 2, and length 3. They have 4, 3, and 1 valid paths respectively. So the result is 8. So similarly in example 2, so the length is 1, 2. So the number of passes correspondingly are 2 and 1. So in together we get 3. So that's the two examples. We will not view the computation process as specified in the explanation in our solution. So that's a note. So let's look at the constraint. So the constraint basically concerns about the rows and the columns. So the rows and columns are between 1 and 1000, and the total number of elements is bounded above by 10 to the power 5. So the range of the element in the grid is greater or equal than 1 and less or equal than 10 to the power 5. So with that said, let's look at the method and the example. So first, let's see the method. So the method is nothing but dynamic programming, right? So here I'm going to initialize a dictionary to store the result. So basically we'll let's call it dp just for convenience of writing. So dp here, basically I will interpret it as the number of valid paths ending at the coordinate ig. So that's the interpretation in our solution. So the natural question is how to update this guy, how to update dpig. So for that, let's look at example 1 to build the intuition, right? So first, so if we look at the top left 1, this is the element in 0, 0 position. So the number of valid paths ending at this 1 is just 1 because it's smaller than all the neighbors. So then similarly, we can have a look at the position here, 0, 1 position, because it's no greater than the neighbors. So the number of passes ending at this position is 1. So let's look at 3. So 3 actually has a neighbor which is smaller than 8. So because the number of passes ending at this 1 is 1, so we can attend those paths with 3. So we get 1 at least. And then if we count 3 itself, it's also 1. So we have 1 plus 1, that is 2. So we have 2 ending at this 3. So now let's look at 4. So there are the 2 neighbors 1 and 3 are less than this 4 in value. So because ending at 3 we have 2 valid paths. So if we append this 4 to those 2 valid paths, we get 2 valid paths ending at 4. So similarly here, so this one, we have 1 valid path ending at this one. If we append that path with 4, we get another path valid and ending at 4. So we get 2 plus 1, 3. Also 4 itself is a valid path. So the update here is 1 plus 2 plus 1. So this are the paths ending at the 2 neighbors with values less than 4, and this is itself, right? So this is the understanding for problem 1. So in total we get 1, 1, 2, 4. That is 8 together. So with that said, I guess the update rule is simple. So for each position, so we examine the 4 direction valid positions. So if that position has a smaller value, we're going to increment the path ending at the position by the number of passes at that index. For example, let's see, we have m and n rows. So if we want to update dpij, so basically we want to look at the 4 neighbors. So if the 4 neighbors, let's see, we have R and C. If the value at RC, so if grid at RC is less than the grid at IG, then we're going to increment dpij by this dprc. The interpretation is very simple. So because for those paths ending at RC, which are valid, we can append the value at index ij, so that we form this number of valid paths ending at ij. So we increment dpij by this dprc. We need to check all valid neighbors for sure. So that's the update rule for this problem. So with that said, I guess we are ready to write the code. So first I'm going to write this big number 10 to the power 9 plus 7, just for convenience, so it's not necessary. Then I'm going to track the information for the rows and the columns of grid. So let's grid 0. So this basically this is sort of a routine. And for this problem, because we are looking at the number of valid paths ending at ij, right? So I'm going to first do a sort. So I'm call this coordinates like ij as coordinates. So basically what I want to do is I want to sort this indices with respect to their value. So it's ij and grid ij. So for I in range m and for j in range m. So this is the thing I'm going to sort. So I'm going to sort with respect to the last element. That is the value. Okay, lambda is x2. So this basically sorted the indices according to their value in the grid. So because I want to first set down the number of passes with the smallest value. So this way we can safely update the grid. So actually, just as a set comment, so this sort is not necessary. So we can write a form of DP without sorting. But I feel that after sorting and doing the update, it's more intuitive. So now we're going to do the DP, right? So DP, I'm going to use const. just to indicate what we are recording. So you can use DP here also. So here I'm going to use collections default dict. So that is int. So if the default value will be 0, so that's the that suits the problem. So you can use the vanilla dictionary for sure. Now we are going to update the DP table or update the counts. So this counts actually, if you can regard it as the cache also. So for result, I'm going to initialize this variable as 0. So whose final state is what we need to return. Then we are going to iterate for ij value in coordinates. Then the count is 1 because at least there's one valid path ending at this ij position, that is itself. Then we're going to examine the 4 directions for RC in I-1j and I+1j and ij-1, I and j+1. Then we need to check if RC is a valid position. So if 0 less or equal than R less than M and 0 less or equal than C and less than N. So if this is the case, we're going to check if grid RC is strictly less than the value. In other words, the value at the position ij. If so, yeah, we can append those valid paths ending at RC by the current value at ij, so that we get this number of valid paths ending at ij. Therefore, according to the interpretation, we are going to update the count by grid by counts RC, right? So you can think of this counts as the DP in the explanation. So once we've done this, basically we set this coordinates counts ij to be the count, right? So then we are going to update our result by the count. So result equals result increment by this count, but we want to modulo this by the large constant m, right? So with that said, we are ready to return the final result. So let's do a special case check for this problem. It passes the first example. So let's also do a let's print out this count to examine the number of passes at ending at different positions. So print let's do a check. You know, the ending at 0, 0 it has 1, ending at 0, 1 it has 1, and ending at 0, 1, 0 it has 2, and ending at 1, 1 it has 4. So same as here, 1, 1, 2, 4. So let's comment this out and do a test for this one. This is a simple example I would say. So we have this one. Let me do a check. It passes the second example. Now I guess it's time to do a generic case test. Let's submit this one. Oh yeah, it passes this generic case. So I would say, so this is the full code for this problem. You are encouraged to try to write a DP solution using different formats, like change the format of the DP table, or eliminate sorting, or using cache. So all are possible. But here we would see, this is the first thought when we see this problem. I guess that's also important. So with that said, I guess that's about it for this problem. Thank you.